engineering at the University of Colorado Boulder. Her research interests include seismic collapse performance, building code provisions for extreme loads, modeling of structures, risks and losses associated with extreme loading, and earthquake performance of buildings. She has her BS degree in Civil and Environmental Engineering from Princeton. She has master's degrees in Engineering and Urban Design from the University College London, and a Ph.D. in Civil and Environmental Engineering from Stanford. I'm glad to have her here today, and please welcome Abbie.
Thank you so much for inviting me to come. So I just wanted to start just briefly with a little bit of background about myself, some of which Linda already said, just so you can know what worldview I'm coming from. So I am an engineer. I want to see now it's not going there. I grew up in Portland, Oregon, so I was really happy when I got a job in Colorado. And I went to Princeton, and at Princeton I studied civil and environmental engineering, but also public policy. And especially the intersection of science and technology and engineering and public policy. So that's been a particular interest of mine since that time. I spent 2 years in London after I was at Princeton, and I studied structural engineering. My background in civil engineering is primarily as a structural engineer, so designing, building, evaluating buildings, but also in urban design and particularly the sort of overlap in how structural engineering relates to urban design and development. And then I was at Stanford and researched. That was really where I got into earthquake engineering. I researched collapse risk of buildings, looking at nonlinear modeling of buildings and how they perform in earthquakes, but then also policy recommendations for how can we get better performance out of our building stock in high seismic areas. And I'll talk about a few questions that we're interested in related to that during my talk. And then I've been at CU since 2008. I'm on the faculty in civil, environmental, and engineering. I just found out I'm going to get tenure, so that's really exciting, like yesterday. So I can stay. And I teach classes in structural engineering, so structural engineering, structural dynamics, earthquake engineering, and I also teach the undergraduate course in probability and statistics and a number of other things. So thank you so much for having me. So I wanted to start with just a definition of what I think earthquake engineering is, which I've pilfered from a number of other people, but it's a lot broader. We give it a really broad definition, actually. So we say earthquake engineering is the estimation of consequences of disaster and the mitigation of those consequences. So we're really concerned with better ways of designing and building, and better ways of understanding what the potential impacts of disasters might be, so that we can plan better for them. We're also interested in solutions of problems caused by damaging event, and I highlighted here planning, designing, constructing, and managing, because earthquake engineers are really potentially involved in all of the different phases in that process. One of my colleagues who doesn't speak English as a first language pointed out to me that earthquake engineering is really anti-earthquake engineering, which I suppose is a valid point. But and I'm really interested in the full range from how we design, how we build, how we decide what we design and build, what regulations apply to what we design and build, and also how do we respond and recover after damaging events occur. And I'm going to focus today exclusively on my work in the area of earthquake engineering, but I've also done, I do some work with snow loads on buildings, so understanding how snow impacts buildings and what we can do to design better for snow loads, and then also I'm doing some work with flood damage also. So the performance-based earthquake engineering is really sort of the framework in which a lot of my work fits. So I wanted to provide an overview of how we do that, and then I was going to talk specifically about a number of the problems that we tried to solve using this framework. So the way performance-based earthquake engineering works is it basically says, well, I have a building of interest. And in this case, I have this building on the Stanford campus, which is fits into a class of vulnerable buildings in earthquakes. It's in older concrete buildings. New concrete buildings are great in earthquakes. Older concrete buildings pretty much stink. This is the geology building at Stanford. It's been retrofitted. That's why I can show the picture and say it's potentially vulnerable because it's not vulnerable anymore. So you take your structure of interest and then you make a computer model of the structure. And computer modeling is something we spend a lot of time working on. In particular, the questions that we're trying to ask, we're not making the type of model that a structural engineer in the design office would make. We're trying to make a model that predicts all the possible failure modes of the structure, and also potentially what would happen to other things in the structure that aren't even really structural engineering. So what would happen to the ceiling tiles or the partition walls if we were to have an earthquake? We then subject our building model to strong motion recordings from seismometers, and we analyze the response of the building to those ground motion recordings. And I'm sure to some of you here, how we use ground motion recordings is going to seem crude and maybe a little bit silly. But one of the things I'm going to focus on is how the types of information we take from ground motion recordings and put them into earthquakes and into our computer simulations models, and what we try to understand from those models. So then we do our dynamic analysis. We predict structural response. You know, we're highly into the nonlinear range of structural response, so we have a lot of problems with convergence and all sorts of computational difficulties in that process. And then sort of the key thing about where earthquake engineering has gone in the last 10, 15, maybe 20 years is that we try to relate structural response now, which, you know, in engineering language, you talk about drifts or forces or stresses or whatever, at two things that we think people care about. So collapse risk, economic losses, potential for business interruption. So this is really sort of the power, we think, of performance-based engineering, is it takes things that we've known for a while about how to quantify structural response and actually relates it to things that people who potentially be interested in, so planners or other types of people. And earthquake engineering has really historically, and probably still is to a certain extent, incredibly reactive discipline, right? So we wait around, and then there's an earthquake, and we freak out. And after Northridge earthquake in California, we're like, oh, we didn't know there was a problem with welded steel moment frames. We better fix every welded steel moment frame. And then, you know, we wait till the next one. And to me, the potential of performance-based earthquake engineering is potentially to allow us to get out of that rut by actually trying to understand ahead of time better what the risk might be and what we might need to fix. It's really been, you know, there's sort of two, I guess, schools of thought of how you could use performance-based earthquake engineering. One is that, like, if you're a client and you come to me and you want me to design a building for you, I could potentially give you some results like this for alternative designs, and you could weigh what is important to you in terms of how you want your building to perform. That, I think, there haven't been a lot of building owners who really are willing to engage at that level of detail. There certainly are some, you know, universities in the Bay Area, organizations with big campuses like Google, where they have, or Hewlett-Packard, that have a huge investment in facilities in high seismic regions. They tend to be interested, but a lot of other owners, you know, they just want a building that meets the building code. And so one of the other ways we've used this concept is to actually investigate our building code provisions. So the building code now says explicitly that there's a 1% chance of collapse in 50 years of a code-designed building. That's new in the last 5 years, and so one of the things we've been trying to do is investigate how well we're actually achieving that goal. So we've really recently decided that we can actually articulate a goal, and then we're trying to figure out whether we're achieving that for all different kinds of buildings. And just, I guess, civil engineering and structural engineering is very different from some aspects of electrical engineering and mechanical engineering, in the sense that everything we design and build is different. Right? Like, it's not like we're producing 100,000 widgets and they're all the same, and then when you find the fault in one, you know the fault in all the other ones. So we have this hugely variable problem where we have this entire existing building stock, tens of thousands of new buildings built every year, and we actually don't really fully know the characteristics of the things that we're trying to analyze and protect. Okay, so I selected 3 or 4 of the studies I'm working on or have worked on. And I want to show sort of how we go through this process of understanding risk in particular contexts. This is a study that I worked on with my Ph.D. student who recently graduated, and we were looking at seismic collapse risk in the Pacific Northwest. And that was of huge interest to us because, well, first of all, I grew up in Portland, so it was personally interesting to me, but also because almost all the earthquake engineering studies that have been done have implicitly or explicitly assumed a sort of California-like context in terms of the ground shaking. And so there really hasn't been much study of what does collapse risk look like in an area where there's a lot of potential for subduction earthquake events. So that was sort of how we started this problem. And then we looked at, strong motion recordings, and we sort of made two critical observations about how strong motion recordings from subduction type earthquake events differ from what I'm going to call crustal events, so of the type in California. So, and we found two really big differences. So one is a difference in duration, and this is not new. People have a long time known that there is a longer duration of shaking at sites from bigger magnitude events. Subduction earthquakes tend to be bigger magnitude events. So we noticed this difference in duration, and we also noticed this difference in frequency content. Earthquake engineers quantify frequency content with spectral acceleration, but it doesn't matter. Basically, we're trying to identify the predominant frequencies of the ground shaking. And so we're identifying differences in duration of shaking and also frequency content. Now, you would think that it would be clear from an engineering perspective what the effect of longer shaking duration was on collapse risk. It seems fairly logical that if it goes on for longer, that you would have a higher risk of something bad happening. But in fact, until we did this study, no one had really looked at that, or rather a lot of people had looked at that and not really come to an answer about how ground motion duration affects structural performance. So the first thing we did is we ran a bunch of nonlinear time history analysis. So this is for 80 strong motion records, ground motion duration on the x-axis. I guess I can use a laser. Ground motion intensity on the y-axis, and you can see that the intensity required to cause collapse of the building is higher for the short duration records, and if you get to a longer duration recording, then in fact you need a much weaker record to cause collapse of the building. So this is sort of inverse relationship between the capacity of, you can think of the y-axis here as the capacity of the structure to resist, you see the downward trend. So the longer the duration of shaking, the longer the duration of shaking, the higher the risk of collapse. And we went through it. I won't spend too long on this, but we went through and we did some mechanics-based understanding of why it is that duration is affecting buildings in this way. As I mentioned, it's a little bit controversial. So we wanted to make sure we really had our ducks in a row as to what was the mechanism by which longer shaking, even of lower intensity, could potentially cause collapse. So we looked at the hysteretic energy demands on the structure and showed that at collapse, they're all equal, but some of them are getting more of the hysteretic energy demand from the long duration shaking, and some of it are getting more from just a high intensity part of the record. So then we went more into the engineering side. We said, well, let's look at some buildings that are designed for 3 locations. And so we chose sites in Portland, Seattle, and Los Angeles. Los Angeles is just sort of a baseline because we sort of have a better understanding about what goes on in Los Angeles. The the x-axis is the building code, and this is just selected building codes, and you can see this is the design value, this is the year. The seismic design provisions have jumped all around all the time. They still are jumping all around. And in particular, there's sort of 2 important breakpoints. So the Cascadia subduction hazard wasn't included in the building code until about 1994. So that's fairly recent in the context of the building stock. If you think about how many buildings in Portland and Seattle were built before 1994, that's a lot of them. And then there's also this important breakpoint here, which is that in the early 70s, that's really when we figured out that it's not all about strength, that there's this really important thing about deformation capacity of buildings and incorporating that concept in the building code. And so there was a change that you can't really see on the y-axis between the 60s and the 70s, where things that are built post-1970 are sort of substantially better in terms of what we think their seismic performance is going to be. So my student basically designed buildings for each of these different time periods at each of these different locations. And what we found is that owners aren't very willing to let us have their drawings for their building because they don't want to know, or they don't want it to be published, what the collapse risk of their building is. So what we typically do is we get the building code, from the 60s. We actually do the design ourselves. We check with some practicing engineers to make sure it's, seems reasonable and the kind of thing that you would see, and then that way we don't step on anybody's toes. So then we took a large set of ground motion recordings. So the subduction are from subduction earthquake events. The crustal is a general set of records which people have used in a lot of other analyses. And then we also use some simulated earthquakes, simulated ground shaking that came from some geophysical simulations. So then we apply those ground motions to a structural analysis model, and we're interested in beams and columns, and sometimes people look at this and they say like, well, that looks like a pretty simple model. It's 2D. It is, and now you're telling me you have some springs in your model. That seems like a pretty crude representation. Turns out reinforced concrete is super hard to model. I mean, it's a really complicated material, and at the scale, time history analyses that we're trying to perform, we're sort of trying to balance computational efficiency, accuracy, and these really sort of large deformation failure modes that we're trying to predict. Okay, so a lot of my research sort of ends in a plot that looks like this. So these are building fragility curves, and the x-axis is ground motion intensity, and the y-axis is probability of collapse. And what you can see, if we look here, so these are the modern buildings, the buildings designed for the 2012 International Building Code. You can see that for a given level of shaking intensity, the collapse risk is much higher if we consider the subduction records than if we consider the crustal records, like significantly higher. This is a big difference. The difference is not as big for the older buildings, and that's just because those buildings are, I don't know, crappy in any situation, and so they don't do very well in either case. So this plot is probably classed as a function of ground motion intensity. In order to say something about collapse risk, we basically have to combine it with something about how likely these ground motion intensities are to occur, and also how likely we are at a particular site in, let's say, Seattle, to get ground shaking from a subduction event as compared to ground shaking from more of a crustal event, because they also have crustal faults in Seattle. So what we did is we calculated the collapse risk, and then we deaggregated the collapse risk by the source, and we found out, in fact, in Portland, 85% of the risk of collapse is coming from the subduction event. That's because they're bigger. That's because they cause longer duration shaking, even though probably the crustal events are more frequent and closer in terms of distance between the site and the source. We also showed, this is a comparison of collapse risk, so you can see those fairly bad older concrete buildings that I was talking about before. These are the newer ones, and you can see that we're predicting actually higher collapse risk in some cases in Seattle and Portland than in Los Angeles, just because of this unique characteristic of ground shaking. And because the building code is now targeting a 1% probability of collapse in 50 years, we're collaborating with people of the USGS who make the seismic hazard maps for design, and also building code officials, and trying to figure out, are these differences worth considering, and if so, how do we implement that concept in a building code document? Okay, so a couple more examples. We've also looked at the characteristics of ground shaking that occur near a fault. So as a fault ruptures, if you are very close to the fault and the seismic waves are traveling in the same direction as the propagation of the rupture, sometimes you get a ground motion trace or velocity time history that looks like this, which has this pulse. And sometimes when you're farther away, you tend to get something that looks like this. And the difference is just because of the seismic wave scattering and bouncing off things. The farther you are, the more it looks just like a random signal, the less you get this high energy pulse at the beginning. So we were interested in the question of, if you get that kind of pulse, how does that affect structural response, and how does that affect structural risk? And in what situations are you likely to get that pulse, if we think it's important for collapse risk? And just a little bit of context here. So we design for uniform risk. So the seismic hazard maps are based on uniform risk, but they are not within about 5 kilometers of the fault. So they're capped within 5 kilometers of the fault. So we were trying to basically figure out what might be the implications of that capping that we're doing in the building code design. So this is we analyzed like 25 different building models with a bunch of different ground motions, all of which had varying pulse periods. So this is the period of the pulse in the ground shaking. This is the first mode period of the building. And we saw that actually, so this again is collapse capacity. It varies strongly with the ratio of the pulse period and the first mode period of the building. And in fact, you see, so resonance is actually the best case. So you get the highest collapse capacity if the period of the pulse and the period of the building line up. And that's because the period of the building changes a lot throughout the analysis, and so it elongates. So as the shaking happens, the period elongates, and it's able to move. In this case, the period of the building is able to move away from the pulsing period. But if the pulse period starts out really big, then as the period of the building elongates, it basically smacks into it and lines up to get a resonance effect. And so similar type of plot, so ground motion intensity, collapse probability at different sites that are closer or farther away from a fault. And this plot is now considering how likely those pulses are to occur, what are the characteristics of the pulses, and that's including seismic hazard information from some of our collaborators. I'm not going to go into a lot of detail there. But what you see here is that the site, if this building is properly designed at a site that's 5 kilometers from the fault, it has higher risk than what we're calling the generic far field case, which is what we typically use in design. And in fact, we found there might be sort of, if you look at the collapse risk in 50 years, it might be like 5% collapse risk in 50 years for a building that's at a location that might get these pulse-like ground motions as compared to 1% in 50 years if you're at a location that's farther away or not likely to get those pulses. We've also looked at the effect of aftershocks on buildings. So as I'm sure you all know, main shocks are often followed by numerous aftershocks. From the perspective of seismic design, we're really concerned with, is there damage to the structure? And if so, is it so serious that we need to prevent people from occupying that building until it is fixed? Or do we need to require repair? So we're interested in this question about, like, based on what happened in the first event, and doesn't need to be a traditional main shock aftershock sequence. It can be any sequence of earthquake events where you don't have time to do anything in between. We're interested in what are the implications for risk if you have an event and you want to know how that damaged building is potentially going to occur in subsequent events. And so here's just a picture. This is actually from an earthquake in Hawaii. So engineers go out and they do this post-earthquake building tagging, where we tag buildings as red, yellow, or green. Green is occupiable, so everything looks good. Red is you shouldn't go in there and you need to have an engineer do a full evaluation. And these are pretty quick evaluations. They're a worksheet with some checks and, not really calculations. And then yellow is that you need more information. And so what we're really trying to do in this study was try to understand if we could help inform that process of building tagging that's being used. Okay. So in this analysis, we now have to consider a sequence of two events occurring. And so we have this set of recordings that we're using to represent main shocks and a set of recordings that we're using to represent aftershocks. And we do, in nonlinear analysis of buildings, we usually take seismometer recordings and scale them all over the place, sometimes with a rationale and sometimes not, but mainly because we sometimes need to look at a case where we can't find the recording for the right case, so we take a recording that is close enough and we adjust it in a way that works for the problem that we're interested in. I'm sorry, lines on this didn't. MATLAB doesn't talk very well to my Mac for some reason. So what we're doing in this case is we have our computer model, we subject it to the first record, we wait for it to stop shaking, and then we subject it to another record, and we see what happens. So we're seeing how the accumulation of damage in multiple events creates potentially increased risk. And this project really started coming out of the first earthquake in New Zealand, or the first big earthquake in Christchurch, and trying to think about, well, what does that mean? And then as there were more and more events in Christchurch, in the Christchurch case isn't actually that interesting for this, because most of the damage was in the second event, right? So buildings that were severely damaged in the second big event were not that damaged in the first event, so we probably wouldn't have picked up anything in this analysis. But that's sort of how this whole conversation started. So this analysis, because we're doing these back-to-back analysis, and we don't really fully understand the characteristics of the ground shaking that we're putting in the first analysis or the ground shaking we're putting in the second analysis, repeat this process like 1,000 times or 10,000 times. And so this is just a selection of the analysis. But this plot is a measure of structural response compared to a measure of ground shaking intensity. And this first one is 1 main shock and 30 different aftershocks, and the second one is 30 main shocks and 1 aftershock. So all of the 30 main shocks were combined with the same aftershock. And so this is showing that when you have only minor damage in the main shock event, how you got to that minor damage doesn't matter very much. So there isn't a lot of path dependencies in that process. But then we go to more moderate or even extreme damage, and you see suddenly, first of all, same type of comparison, but now we're still seeing a lot of variability in both results. And I guess this plot also emphasizes we're dealing with something here that is hugely uncertain. You know, when we try to characterize uncertainties, we have coefficients of variation of 60 or 80%. You know, so we're dealing with things that are highly variable, and we're trying to understand something about them anyway. So this, again, a fragility curve, ground shaking intensity, probability of collapse. And this is showing that if you only have a little bit of damage, you basically aren't changing your collapse risk at all. But then as you get to higher levels of damage, so these two are higher levels of damage, you start to see this curve creeping to the left, which means that your median capacity of the building is going down or the collapse risk is going up. Okay, so then these are the tags that we use to tag buildings after earthquakes. So inspected, restricted use, and unsafe. Of course, we never call something safe. That's risky for us. And this procedure by which we tag buildings was developed in probably the 70s and hasn't really been advanced that much. And it's intended to be really simple. You know, it's intended that every civil engineer in a city can go out with a clipboard and actually inspect a lot of stuff in a relatively short amount of time. But we were interested in knowing sort of how well that building tagging procedure was doing. And so one of the things is we looked at a lot of different measures in our model of damage, and then we compared them to what those worksheets says and tried to understand, does the worksheet have the right trigger points in terms of once the residual inter-story drift gets beyond a particular point, this is the tilt, the permanent tilt of the building. Once it gets on a particular point, how much does that change your collapse capacity, and how much are we prepared to deal with some additional risk after an earthquake versus how much do we want to limit from entering into their buildings? Okay. So I'm also doing some work with regional seismic performance. So everything I've shown so far is we looked at a group of buildings and we tried to say something about that group of buildings, but we didn't really consider them as a whole. So this is the inventory of concrete buildings in Southern California. And the left plot is ground shaking intensity predicted by the shakeout scenario in Southern California for a magnitude 7.8 potential earthquake on the Southern San Andreas Fault. And then this is our prediction of what would happen to concrete buildings in that type of event. And the situation with concrete buildings in Southern California is highly changing. So when I started my Ph.D. and I started working on older concrete buildings and worrying about their vulnerabilities, nobody was doing anything about it. The mayor of Los Angeles announced in December that he wants to have a mandatory retrofit law. And so there's a flurry of activity right now about what does that law look like and what can you require owners to do. But basically their concern is that if you had a scenario like this one, you know, downtown LA is somewhere in here. There's a lot of red, and red is bad in that part. And so there's a concern that in a big earthquake, certain parts of the building inventory would be really heavily devastated. So we then overlaid the inventory of concrete buildings on this map. So we're trying to show sort of there's like 1,000 of these in Los Angeles. You know, there's a few in San Bernardino, some in Riverside. Building inventory is another interesting thing because most cities actually have no idea what they have in their building stock. You know, they have plans somewhere in the basement, but unless you're prepared to go through every single plan that's ever been submitted to the planning department, they can't even tell you whether they have concrete buildings or steel buildings. The system by which they're keeping track is not very. Let's say it's outdated. So these blue circles, I'm not responsible for the blue circles for inventory, but actually a group of engineers has been going basically sidewalk survey every city in California, trying to understand how many of these buildings that they have. I wanted to highlight a couple other things that I'm doing, which I don't have slides for, but we are looking right now the potential for induced seismicity to cause building damage, including chimney damage and some other things. So we're looking at recordings from induced or potentially induced events in Colorado and elsewhere, and trying to understand how that might change the picture that we're looking at. And we, earthquake engineers are really into simplification, right? Engineering is all about like, oh, we don't know what that is, let's multiply by a factor of 2. But one of the things that we've ignored for a long time is the vertical component of ground shaking. So we've worried a long time about the side-to-side component of ground shaking, how that affects buildings, because we design buildings for gravity, so they should be doing something well in the vertical direction. But actually we're finding that there are certain types of buildings that if you consider the fact that the earthquake is shaking the building up and down as well as side to side, that actually changes your understanding of what risk looks like. And that's it. So my research is funded in National Science Foundation, USGS, National Institute of Building Sciences. And obviously, I did very little of this work myself. All the credit goes to my students. So, thanks.
Questions?
Could you elaborate a little bit about how the 1% risk of collapse in 50 years is calculated?
Yeah. So until 5 years ago, we designed for the uniform hazard. So we designed for the ground acceleration that occurred with 2% likelihood every 50 years. And then we decided that that probably wasn't good enough because, in fact, uniform hazard doesn't really give us uniform risk. And so then there was this move in the 2010 version of the building code to move to this concept of uniform risk. And the way we're doing uniform risk is that we have seismic hazard information, we have generic information about how we think modern, well-designed buildings perform, which is based in some science, but it's obviously a simplification because not all buildings perform the same. And then we basically are convolving those two pieces of probabilistic information together to get a collapse risk. And what happens is if you do that and it doesn't satisfy the objective, then we change the design value, which changes our estimate of building performance, and we tinker with that until we get consistent risk.
So does that imply that if a certain amount of ground shaking happens, that 1 out of every 100 code design buildings will collapse? Is that kind of what it means?
Yes. And I think almost everybody thinks that probably buildings perform better than that. So modern buildings at least. But we don't, that's the best estimate we have been able to get based on the current science. And I would say, so the people who are responsible for these new design ground motions that are risk targeted, it's the Seismic Hazard Mapping Group in Golden at USGS, and they are well aware that we haven't fixed all the problems. But just by going from uniform hazard to uniform risk, even if our estimate of risk isn't right, we fixed a number of problems that we were having by designing for uniform hazard. So it's sort of it's a better way, but certainly not a perfect way. Yeah.
One more detail, that Stanford building you showed was the geophysics building.
Geophysics.
Geologists are smarter than that.
I was curious in your analyses of how you kind of model the foundation of a building, and do you take into account the soil matrix and any of that? Do you just kind of slap a coefficient on there, and then are you mostly looking in the building itself?
So in the results I showed here, I'm mostly looking at the building itself. I'm collaborating with one of my colleagues at CU, her name is Pj.D. She's a geotechnical engineer, and we are working on some problems related where you really can't ignore the soil to the extent that we've ignored it here. So liquefaction, impacts on building damage, but I don't have any of that to show here. Yeah, that's the modeling of the soil is a really complicated problem.
I actually had 2 questions, and he just asked one of them. I was specifically wondering if liquefaction and things like that were built into the models. My other question, just so I understand this right, is when you first started showing the slides of subduction, earthquakes, and the effects versus what you were calling the crustal events, the duration of the shaking is longer for the subduction ones, but the accelerations were actually much higher for the crustal ones. And so basically I just want to make sure I understand that in terms of the collapse potential for a building, it's actually more related to the duration of the shaking than it is the actual acceleration?
So it's primarily related to the acceleration, but duration actually has an important influence. So what it's saying is that even though the subduction shaking tends to be lower acceleration, lower in intensity, because duration is important enough that basically some of the benefit from having that lower intensity goes away. So, so basically it's saying that there really are these two factors that are really important, and that knowing something about duration really affects how likely you think a building is to collapse. So if you were to so when I showed the deaggregation of risk with subduction and crustal events, that has the seismic hazard information built into it. So that knows how likely the different accelerations are to occur. And so even though the subduction earthquake causes, on average, less intense shaking, the fact that it also causes, on average, higher, longer duration, that it still ends up constituting the majority of the risk, if that makes sense.
Yeah, so those curves that you showed integrated those two things.
Yeah, so we were trying to, and the one that we've done a good job dealing with sort of historically in earthquake engineering and building code design is the acceleration piece. And so that was, so basically, we would think of what the question we were trying to ask is what else do you learn when you add in this component of duration and try to understand the impact.
I got another one.
Yeah.
So I work primarily in internationally, and I have a lot of interaction with buildings that aren't as to code as the United States. Do you ever collaborate with Bernard Abbie and do engineering for developing communities, or do you ever take into effect, brick buildings?
Yeah, absolutely. So I have done some work in developing countries, and I've done a lot of work in trying to understand building codes. And, most countries have good building codes, actually. There are some exceptions, Haiti being one of them. But there's also huge problems with implementation and enforcement. And so, one of my students is working right now in trying to understand concrete buildings and seismic risk in a part of India that has landslides and earthquakes that cause landslides, and buildings that are built on hills, and, a culture of building where you just put in enough steel until the inspector leaves, and then you take some out, and then you finish pouring your concrete. And so, so we're also looking at that problem. Factors there are way more economic than technical, and cultural than technical. You hear a lot you always hear stories like an earthquake in Turkey, for example, of oh, well, that column fell down because the guy who built it, his shoe was in it, and then he pulled his foot out and left the shoe, so then the column was missing, 3/4 of its concrete in the place where the shoe was, and and that's a much bigger problem than understanding the building code itself, because Turkey has great building codes. So it lends itself to different kinds of questions. And I've done some work with brick building. Brick is a really hard thing to understand. We did some studies of brick buildings, and we're trying to do more, but haven't gotten particularly far on that yet.
I had one question. So I guess a while ago they started putting seismometers in the tops of tall buildings, and they realized that the coupling is very different, or the signal is very different, and so they need to really consider the coupling of the ground with the entire building. Has there been much advancement on that, or? And I know USGS has been trying to put in more in buildings. I don't know if you're involved with looking at those recordings, or.
I haven't been. I mean, I know certainly some of my colleagues have been, trying to compare results of computer models. Like I have 2 results from buildings where they have seismometer recordings over the height of the building, and trying to understand what that tells us about building performance and what we can learn from them. It turns out that there are a lot of things about buildings we just don't understand that well. So even a concept like damping, which from a physics perspective is not that hard to understand, but how to quantify damping in a building model, we're not very good at that. And so some of the recordings that we've had have helped advance that kind of thing. So certainly more information is better. We're also very limited by the total number of recordings. I mean, one of the reasons that nobody had looked at subduction effects before we did was because until the Chilean earthquake, there weren't enough strong motion recordings of the type that could be used in structural engineering analyses, the Chilean and the Japanese and the Sumat. So all those events that occurred around the same time, there weren't enough recordings to actually do anything with. So we're also just limited generally by what the information we have, and a lack of strong motion recordings in dense urban areas.